All right, y'all, welcome to week 3 of Advanced Instrumental. So this week we're going to take a little bit of time and go through some components of optical spectroscopy instruments that might be new to you. And we'll do this through 2 videos. The first, a look under the hood, part 1. So key concepts for this week's videos are to understand the rationale for optical instrument design and describe the function and behavior of some of the components that you might find in instruments that use radiation from the IR, visible, and UV regions to interrogate a chemical system. All right, so we call optical spectroscopy, of course, because we are using light to interrogate a chemical system. And so there are a couple of different ways you could set up an instrument to do these kinds of measurements. It's a pretty broad field if you think about really the only classification we've put on it so far is that you have to use light to stimulate some sort of observable change in your chemical system. And so some of the ways that this is done, I've got 6 listed, will hopefully be old hat for you, while some of them might not be. And I just want you to kind of think about that as I write them in. So the first one is absorption. Hopefully most of you have seen this before. The next is fluorescence. The next is phosphorescence. Okay. Then I've got scattering spectroscopies, things like Raman spectroscopy, just general emission spectroscopy, and then chemiluminescence is my last one. So hopefully some of these are not new to you. We're going to specifically in this week going to be talking a lot about fluorescence and Raman. Just for, we would love to touch on everything, but this is an 8-week class and I'd rather have you go deep on a topic than wide. So we're just going to pick a few and sort of dive in. All right, so I was mentioning that really the only classification we put on this type of instrument is that you have to use light to elicit a change in your chemical system. And so instrument configuration can really differ, but most of the components that are used are really similar because of the narrow range of electromagnetic radiation that we are using to interrogate our system and then probably thus detect. So, we're thinking like 400 to 800 nanometers, right? It's not a huge swath of the electromagnetic spectrum. And so a lot of the components that we use, no matter where they sort of are the same. So let's take a look. In general, typical spectroscopic instruments have 5 components, though where they are located within a particular instrument can vary. So the 5 components are, of course, a source of radiant energy. This is your light source. Okay. The next is a container for holding your sample. The next is a device that isolates a restricted region of the spectrum for measurement. So we call this a wavelength or wavelength selector. So the purpose being to select a narrow band of electromagnetic radiation. And you'll see that we can use these sort of early in the instrument or late in the instrument. In both places, the actual elements that you're using are pretty much the same, but they are sort of there for different reasons. So it's kind of a fun component to think about. The next is a radiation detector. So I'll use an example from absorption spectrometry. So the goal here in absorption spectrometry is to measure is to compare the intensity of a particular wavelength of radiation before it hits a sample and then after it hits a sample, and the comparison of the intensity of those two signals tells you how much light was absorbed by the sample that comes between those two measurements. And so the goal is to detect the radiation that's coming out of the sample, like how much of that radiation that was initially there is now left after it has hit the sample. And so a detector for that would be useful. And then the last thing is a signal processor. So if you think back to week 1, this is something like a readout transducer. Readout transducer. All right, so I want you to take a look over on the right-hand side of this slide, and there are 3 panels, A, B, and C. A, B, and C. And I want you to pause the video for a minute and think if you can determine what kind of measurements from this list over here on the right or on the left, what kind of measurement is being made by each instrument in each panel. Right, so hopefully you pause the video and you did that sort of thought experiment, and probably what you came up with is that panel A is an absorption measurement. That is what that instrument can do. So if I think about it, I have a light source, usually first in our instrument schematic drawings, then a wavelength selector. So if you remember back to when you learned about Beer's law, you know that Beer's law sort of falls down if you use polychromatic radiation. And so a wavelength selector right after the source of light gives that monochromatic light that's required for an absorption measurement. That light of a particular wavelength comes out of the wavelength selector, hits a sample. The detector will detect the intensity of the light that comes out of the sample, looking, and again, remember, we're looking for the attenuation of the intensity of light after it hits the sample. So that's what that detector is coming up with. And then you have some sort of signal processor with a digital readout, right? That readout transducer. So that's an absorption measurement. In B, we're looking at fluorescence. So a tip-off should have been the 90-degree bend in this instrument. Notice that the absorption measurement instrument was a pretty straight line. The fluorescence measurement in part B is intentionally at a right angle to the source of light for this measurement. So let's sort of go through it. We've got a source of light here. We have a wavelength selector here to select monochromatic light from polychromatic light, if that isn't necessary. Then that light, that monochromatic light, will hit the sample. Remember back to when you were first learning about chemical measurements in your undergraduate degree, that generally speaking, fluorescence is the entire point, right, is that a molecule is hit with a photon of a particular energy level that electronically promotes that molecule to an excited state. And then fluorescence is the radiative decay of that molecule's energy from that excited state to a ground state. And so the radiative decay is the important part for a fluorescence measurement, simply because that means that you are emitting a photon of a known and particular wavelength. And so the goal with a fluorescence spectrometer is to detect those emitted photons rather than the original source photons. And so this wavelength selector will help us select the wavelength of the emitted photons and the detector will detect how many of them, of those emitted photons, are coming from that sample. Again, we have a signal processor, a readout transducer at the back end of this instrument. The last panel, panel C, is indeed just an emission measurement. So this is where you might have something like a flame atomic absorption spec, or sorry, flame atomic emission spec, where you're looking for the emission of a particular wavelength from a metal, let's say. And so you've got your flame, which atomizes and ionizes your metal. Your sample is down here in this little beaker. You are doing that atomization and ionization in the flame. You're selecting a particular wavelength to observe that's equivalent to the energy of photon that is emitted by that metal as it returns back down to an electronically grounded state. And then that detector here is going to detect how many photons are actually coming off of that flame. So, like I said, all of the components are there, but the position varies, and the reason for it being in a particular spot varies. And so one of the things that we'll ask you to do this week is to design a flow cytometry, the optical system for a flow cytometer that is capable of flow cytometry. And it's going to be a fluorescence measurement, right? Or actually many fluorescence measurements, sort of all at the same time. And so it's a really cool way to sort of apply the knowledge that we're going to gain in this couple of videos. Okay, cool. So one of the ways that I want to continue talking about this is we have to talk about the transmission of electromagnetic radiation, and we have to talk about the individual components that are going to sort of make that happen. So the next couple of slides are simply a reference for you. So I want you to think that there are a number of components that are always sort of the same, right? We just talked about those: the source, the container, the wavelength selector, the radiation detector, and the signal processor. So here are some examples of those 5 components and where in the electromagnetic spectrum that they are actually useful. So for example, in the first half of this table, we've got materials that you could use for cells, like containers for your sample. If you're thinking about doing anything in the ER, maybe you've used a salt plate, sorry, in the IR, not in the ER. Maybe you've used a salt plate before in an IR instrument, right? That makes sense. If you're going to be in the, UV, and you're going to be making some sort of UV measurement, a quartz cuvette is very common, that sort of thing. Okay, so this is how I want you to just use these tables to your advantage as you're thinking about possible components that could be put into an instrument. Another grouping, of course, that we just talked about was wavelength selectors. So there are lots of these, lots of really cool ones. You can split them into 2 categories. The first is continuous, the second is discontinuous, meaning some will allow through many wavelengths of light, and some will allow through varied and not very many wavelengths of light. And so that's what we're talking about with continuum or versus discontinuous wavelength selectors. The next is sources. So this is sources of radiation. If, again, you're looking for a continuum, many wavelengths of light to be used, or a discrete short number of wavelengths that you need to use for excitation of your sample, those are called line sources. And we'll talk about all of these different kinds and what they mean in this video and in subsequent videos. I think the last one I want to talk about is detectors. And so there are a couple of different ways that you can detect radiation, right? You can actually detect the photons by using, a photographic plate that's old school. Slightly less old school is a photomultiplier tube. Probably even less old school is something like a charge transfer detector or a CCD. CCD meaning, sorry, that's should not throw out acronyms without defining them. CCD is a charge coupled device. Basically acts as a camera, just like the one on your smartphone. Other options are thermal detectors. So we know that light can be converted into heat. And so you can have things that deal with changing pressure as things heat up. Similar thing, you could use just a temperature change across a detector to measure voltage, like a thermocouple. So we'll talk about a couple of those options as well in the course of these videos. All right, so the place I want to start is radiation. And the reason I want to start here is because if I go back to my instrument schematics, you'll notice that almost 100% of the time, the source is the first part of the instrument, right? So let's kind of go back and start at the beginning. All right, so remember that I said that sources of radiation can be continuum sources or line sources. And so a continuum source is one that emits radiation that changes in intensity smoothly as a function of wavelength. And so the examples that I've given here are a deuterium arc lamp and a xenon arc lamp. And so we'll talk a bit more about how arc lamps work. But the idea is that there's a change in intensity that's relatively smooth, right, as a function of wavelength. So this is a relatively sort of smooth change. The same thing over here for the xenon arc lamp. This is a relatively smooth distribution across wavelength. Okay. You can have continuum line sources, which is just a combination of both of the types that we'll talk about. And you could argue that you might have a line source in some of these where these really intense and narrow spikes happen over in the lower energy spectrum, part of the spectrum. All right, so let's talk a little bit about how an arc lamp works. So I'm going to talk specifically about deuterium, though I think you could probably pretty easily make the jump to hydrogen here. So a deuterium lamp operates by forcing an electrical discharge through a normally non-conductive medium that produces light. So over here on the right, some examples, right? I've got couple of wires here that aren't attached to each other, but there's a passing of electrons across air, which is normally insulative and non-conductive. And in doing so, there's a release of light. Okay, and we'll talk more about how that happens. Other examples that you maybe you've experienced, I'm not sure. If you have a living room outlet that's not well insulated, you could have an arc. So this would be similar to like if you plug in a lamp or a vacuum or something and you see like a spark at the outlet, that's an arc. Okay. All right, so let's talk about what an arc really is. So an arc occurs when you have a discharge of a photon. And so you can see, we're going to work our way backwards. There, you can see that there's a discharge of a photon here in this from this deuterium energy spectra scheme here. So what I have is deuterium that is going to somehow have energy added to it. Okay, so this E sub E is the energy added to the D2 molecule. Okay. The result is that you end up with an electronically excited deuterium molecule. Very exciting, very exciting. As this as this molecule relaxes back down to ground state, it will break apart to give the individual deuterium atoms, right? So that's this guy and this guy, that have unique kinetic energies. Okay? And so they may not have transferred all of the energy related to the amount originally absorbed into kinetic energy. And if they don't, there's some left over, and that gets released in the form of a photon. All right, so let's give this a little bit more specific of an energy equation on it. So E sub E, right, that's the energy added to that deuterium molecule, is equal to the energy of that excited deuterium molecule, which is equal to the energy of the first deuterium atom plus the energy of the second deuterium atom after that molecule has split, plus any energy that's released as a photon. Okay, so as this molecule splits and releases energy, there does not necessarily have to be an even distribution of energy between these two terms. And so really, this photon can have any energy that is equivalent to, could be anywhere in the range from the energy of that very initial excited deuterium atom all the way to 0. Okay. So the energy and the frequency of this photon can vary continuously. Okay. And that is how we get a continuum source. Okay. Pretty fun stuff, right? All right, so the other common kinds of source radiation that you might find are line sources. So the cool thing about line sources is that they emit a limited number of lines or bands of radiation, which span a very limited range of wavelengths. And so a couple of examples that are common in spectroscopy instruments are a hollow cathode lamp. You'll find this in atomic spectroscopy, mostly because when we are looking to excite a metal in a flame, right, in order to get that, to get an absorbance measurement. So I'm thinking specifically of FAAS, flame atomic absorption spectroscopy. We're looking to see how much the metals that are in a particular flame, how much radiation that they can absorb, and it's the amount of radiation absorbed is of course proportional to the concentration of the metal in the flame. And so if you were looking to only put, instead of having to use a monochromator right after the continuum source in order to get that monochromatic light, what you could use is a hollow cathode lamp or another line source that specifically has emits radiation of a very narrow wavelength range to sort of shine on those metal atoms and ions in the flame in order to get that absorption measurement. All right, so another example you probably have at least heard of is a laser. So these are used all over the place. I could say that they're used in molecular spectroscopies, but of course they're used in atomic spectroscopies too. So they're just really ubiquitous. Okay. But the goal here is, of course, to produce a coherent beam of a narrow range of wavelengths of radiation. And we'll talk a lot about how lasers work in just a little. Before we do that, I want to sort of come back to hollow cathode lamps, just in case you've never encountered one before. So atomic absorption techniques are really highly specific because atomic absorption lines are super narrow, and because electronic transition energies are unique. And so we use a hollow cathode lamp, which emits a really limited number of radiation lines or bands. So the point is that each line or band of radiation that a hollow cathode lamp can produce has a really limited range of wavelengths, which is great for an absorption measurement, right? That way we don't have to use a wavelength selector right after a source in order to get that monochromatic radiation that's necessary for an absorption measurement. So the way that a hollow cathode lamp works is you have this glass body. So let me just, you have this glass body of a lamp, okay? The inside is held at a pretty low pressure. So for reference, right, 1 atmosphere of pressure is 760 torr. So you're pretty low. You've got an anode and a hollow cathode. That's where the hollow cathode lamp name comes from, right? And so basically what we're doing is we're going to force an electron to move from an anode to the cathode. And in doing so, because there's not much in, so that we're holding the inside of this glass lamp at vacuum, but there's going to be an inert gas inside that lamp, right? We're not at complete vacuum. And so basically what's happening is that you are going to apply a voltage across those two electrodes, right? The anode and the cathode, in order to force a current, usually 15 milliamps, not super crazy. The voltage that is applied is sufficiently large that the gas inside that inert gas acquires enough kinetic energy to dislodge some of the metal atoms from the cathode surface to form an atomic cloud. Okay, so, and that we call that sputtering. So let's back up just a minute. So I'm going to apply voltage across these two electrodes, and in doing so, I'm going to introduce enough kinetic energy to that gas that's there, so in this case, argon, that it's going to run into this hollow cathode, right? That's the depiction of this sort of like U shape on its side. This is the hollow cathode. It's going to dislodge metal from the hollow cathode, and it just so happens that when we are doing an absorption measurement, we are going to have a hollow cathode made of the metal for which we are trying to make a measurement. Okay, so for example, if I wanted to measure the amount of calcium in my sample, I would make sure that there was a coating of calcium on the hollow cathode in my hollow cathode lamp. All right, so the result is that you dislodge some metal from that hollow cathode. The gas still has some kinetic energy, right? Other atoms will still have that kinetic energy. So if those interact with your dislodged metal, they'll take on charge, become excited, right? And then when that metal returns back to ground state, it will produce a photon of a particular wavelength. Okay, so you are sputtering the metal off of the hollow cathode. You're exciting it through the interaction of that kinetically excited inert gas, and then you are looking for the emission of a photon from that metal as it returns back down to ground state. All right, so that's sort of how a hollow cathode lamp works. Let's see, the next, right, so that's one of the line sources we talked about. The other was lasers. If you're not in the know, you should know now that laser is actually an acronym for light amplification by stimulated emission of radiation. And so this is an image of how a laser actually works. So lasers produce intense light through amplification. So they make use of energetic atoms that are in a medium. So here's my medium. Okay, so we'll talk about how atoms in this medium gain energy, but they do. And so we make use of that energy to sustain and build laser beams. So notice that on either end of this sort of column, I have two mirrors. And so basically what I'm going to get when I have an operational laser is a self-propagating wave of coherent photons that are sort of bouncing back and forth between these two mirrors. And every time they bounce back and forth, they go back through that active lasing medium. Anything that's not coherent, meaning that it's not in phase with the sort of propagating wave, is considered non-parallel radiation, and it gets dumped out of the lasing medium and is no longer useful. Okay, note that on the right-hand side of the active lasing medium, there is a partially transmitting mirror. This is how you get a laser beam out of a laser, right? That makes sense. You can't just have the propagating wave going back and forth inside this cavity forever. There would be no way to get it out. And so a partially transmitting mirror allows for some of the wave as it sort of moves towards the right. Some of it will bounce off and go back towards the left, but some of it will go through. That's why we call it a partially transmitting mirror. Okay. The active lasing medium, there's so many different ways that you can produce a laser these days, right? You can have a solid crystal like a ruby. You could have a semiconductor. You could have an organic dye. You could have a gas. There are lots of different ways and lots of different reasons why you would probably use each kind. And so we'll talk about that in a few slides. But before we get there, I kind of want to talk about how we get this laser to actually produce radiation of a particular wavelength in a coherent manner. And so we're going to talk about how lasers function in general, and then we'll jump into sort of specific kinds and types of lasers. All right, so many of you probably this is familiar. The Maxwell-Boltzmann distribution is that on average, you have a number of atoms n sub I that will be in an energy state E sub I. So let's draw what I mean. So I'm going to give you some labels first. So if instead of using I here, I'm going to use, well, no, I should probably continue to use I. Never mind. I'll leave that there. Okay, so if I have a ground energy state and let's say an energy state equal to E sub 1, generally speaking, Boltzmann's distribution says that at low temperature, most of my atoms, molecules, whichever you like to think about, are in a lower energy state. But a few will be promoted to a higher energy state. So here's E sub 0 again, here's E sub 1, E sub 2. So I had 5 over there, so I can put 5 here. So maybe this guy moved up here. Maybe this guy moved up here. Okay. So I've got, in this depiction, I've got 2 out of 5 that are in that higher energy state. In reality, the Boltzmann distribution says that on average, a number of atoms, n sub I, will be in any excited state with the energy E sub I. Okay, so let's put an equation on that. So n sub I will be equal to a proportion of the total number of atoms or ions in that system multiplied by e to the negative E sub I over the Boltzmann distribution constant multiplied by the temperature in Kelvin. Okay. So I should probably give you some number of atoms, and I is the number of atoms. E1 T is temp in Kelvin, and K sub B is Boltzmann constant. All right, so the consequence of this mathematical relationship is that the higher the energy level, right? The higher the energy level, the fewer atoms or molecules that will actually be in that high energy state. Okay. So here, I want you to consider there might be a second energy state. Let's call it n sub j. Okay. In n sub j, well, I should say that there are n number of atoms or atoms or molecules in this level with energy equal to E sub j. Okay, so let's call this E sub O, where there was E sub I before. And so from this very hastily drawn diagram, you can see that the energy of that higher energy state is bigger than the E sub I that we were talking about earlier. Okay, so in this case, we can relate the number of atoms or molecules that make it up to E sub j by considering the relative number that were in n sub I, or sorry, E sub I. So n sub I multiplied by E multiplied by the energy in that J level, negative, over Boltzmann constant multiplied by temperature in Kelvin. So the ratio Nj to Ni, okay, occupying so this is the ratio of the number of atoms that occupy those two states. I can write as E to the minus E sub j over Boltzmann constant times temperature over E to the minus E sub I over Boltzmann times temperature. All right, so in this case, remember that the transition from I to J has a corresponding energy change. So EJ minus EI is that corresponding energy change. And it's accompanied by the release of a photon, right? So as the molecule goes from one to another, right, down from EJ to EI, there can be the release of a photon. So this would be a radiative process. And so the energy of that photon is the difference from J to I. So just to make it more complicated, no, I'm just kidding. But if that's true, then I can write that the relative population in energy level J can be described as Nj equal to Ni multiplied by E to the negative, and then we can insert the energy of the photon that's released here, right, over K multiplied by T. All right, so I can get the release of a photon of a particular energy through the radiative decay of an excited state molecule from one state to another. And the probability that will happen is described by this natural Boltzmann distribution. Okay? So that's what we're talking about, the probability of that to be true. So you might be saying to yourself, okay, that's fine, but how do those energy levels actually change? How do we move atoms or molecules through those energy levels, cycle them through? And so I'm gonna draw a picture, another picture. So here's my ground energy level. Okay, I'm gonna give us 4 atoms or molecules here. Here's E1, EI, it doesn't matter. They're the same. And notice that if I'm talking about a molecular laser rather than an atomic laser, I might have additional vibrational or rotational energy levels above E1, but I'm talking about that electronic transition here. So I'm going to hopefully excite my ground level atom or molecule, in this case molecule, because I've drawn those vibrational energy levels in, to an electronically excited state. Okay, so, oh geez. What that actually looks like is here's my atom or molecule, okay? I have some photon of particular energy incident upon it, right? It's gonna hit it and keep going. So this was originally at EO. After this process has happened, now my atom or molecule is excited, okay? And it's in that E1 or EI state. This is, of course, what we call stimulated absorption, right? That's how we make the jump from EO to E1. There is, I think, a not too complex of a leap way to get rid of that extra energy, right? It's less stable than it should be or could be. And so to get rid of that extra energy, you go back down to ground state through the emission of a photon with energy equal to the energy of the original incident photon. This, of course, is what we call spontaneous emission. So one photon in equals one photon out, okay? But what the principle of how a laser works is that there's another option here. So another option exists. That option we call stimulated emission. So I want you to consider that we have our excited atom or molecule in the E1 state. Consider that a photon of equal energy to the first photon that hit it is again incident upon that already excited molecule or atom. And so the process that happens here is that your atom or molecule goes back down to the ground state. That's where it feels most comfortable, and that's where it should be. And in the process, it emits two photons of equal energy. Okay, this is called stimulated emission. And really, the reason that lasers have the word amplification in is because this is how we get from one photon in, two photons out. Okay. All right, so if a photon of equal energy interacts with an already excited molecule, that atom dumps its excess energy in step with the incoming photon, right? So that's why I've drawn them sort of exactly one on top of another in the same phase, right? So the important part here, what's important to note, is that emitted photons in this sort of paradigm of stimulated emissions are in phase they are with each other. They have polarization. They have the same polarization. And they propagate in the same direction. So this is important because if you're trying to build a self-propagating beam, you want those things to sort of work together, those photons to sort of work together to build that self-propagating wave. So the bigger the wave, right, the more laser power you'll have. All right, so an example of what I just drew is here. This is from Principles of Instrumental Analysis. So you're ending up with, you're starting out with a molecular atom in that, oopsies, I should not use that, of that excited state. You have an incident photon of a wavelength that is the exact difference between EY and EX. And so the result is the emission of those two photons as that atom or molecule relaxes back down to the ground state. Okay. This wave, right, can combine together. So these two photons are able to hit this next excited state, right, to an excited state atom or molecule to emit another two. And so you can see how the power of this wave just sort of grows and grows. So this is stimulated emission. Exciting stuff. All right, so probably what's on your mind, what should be on your mind, is how likely is this to happen? And so hopefully you can remember back to when you took your second semester quantum course. And you can think back to Einstein's A and B coefficient proofs. I'm sure that we talked about this probably in physics as well. But the probability of stimulated emission is identical to the probability of stimulated absorption, right? You're just as likely to have stimulated emission, have a photon hit something that's already excited, as you are to have something sort of spontaneously emit a photon once it's been excited. So the probability of spontaneous emission is inversely proportional to the probability of stimulated emission. So interestingly, you can write it like this. Ooh, no, not like that. So I'm going to give you some definitions of some variables first. So A, I'm going to call spontaneous emission. B is stimulated absorption. So A over B is equal to 8 pi HP nu 3C3. Okay, so this is a 3. Okay, so the problem here is that normally, right, if you think about this inverse relationship, the problem here is that normally we have more atoms in the n sub I state rather than the n sub j state, right? That's what the Maxwell-Boltzmann distribution told us. So stimulated absorption is more likely than stimulated absorption. That's not great because that means no laser, right? But we can, if we could get a substantial number of atoms to be promoted to that upper level energy state so that it was more likely to have stimulated emission rather than stimulated absorption, then we could have a laser. And so the way that we do this is through a technique called population inversion. So, right, let's think about this. In order to have a laser, the number of photons produced by stimulated emission must exceed the number lost by absorption. All right, so let's draw a picture. Here's my ground state. Here's my excited state, or my lower state and my higher state, however you want to write that. Probably higher and lower. I've got something in the lower state here, a particular number, an atom or an ion or a molecule. I'm going to promote it via something we call pumping, and I'll get to that in a minute. I'm going to promote it to the excited state. Okay. What's going to happen next is a fast non-radiative decay. So this is a fast non-radiative decay of radiation. So we're losing a little bit of radiation. In general, it's going into the crystal lattice of the active lasing medium. Okay. What's happening, right? So we're going to be actively moving ions, atoms, molecules from this lower energy state into this higher energy state, and they will be quickly sort of degrading into this slightly lower energy state, which I'm going to call E sub x. Okay. The interesting thing is that this E sub x level is sort of a metastable state, so that you can grow a population of excited atoms, molecules, ions in that spot. Okay, the time scale here is like a millisecond, right? The goal is that you have more of your lasing medium in this energy state than you do in this energy state, right? And that is how we get that population inversion, because Maxwell-Boltzmann distribution tells us that in general, we should have more of our lasing medium here. But by pumping, by actively exciting a large proportion of our active lasing medium into this metastable state, we can grow the population of excited atoms, ions, molecules in order to get the ability to lase. And so what happens then is the emission of photons equal to the energy change from E sub x to E sub 0, right? This is lasing. We're going to apply energy of an amount equal to E sub x minus E sub 0 to stimulate emission of the photon from the excited molecules, ions, atoms in E sub x. Okay. This is what we call lasing. This is lasing. Yay. Okay. So let's look at the image over to the right. So the sort of light gray box is my active lasing medium, and the two solid lines on either side of it are my mirrors. Okay. What I'm doing is I'm going to give energy to my active lasing medium, and you can do this in a number of ways. Commonly, these are pumped optically, so you're just going to shine some light onto it, and that's how you'll give it that initial pump energy to promote the active lasing medium to an electronically excited state. When that happens, you're going to have photons from that pump energy that are going to go through the process of stimulated absorption, but then some of them will also have stimulated emission happening from photons that are being emitted by the pump energy source. So the goal or the outcome here is that eventually you'll have them sort of grow a propagating wave. So some of those photons will kind of happen in a non-discriminate way, and we don't care about those, they'll go away. But as these photons are emitted, more and more of them will be in the same direction that we want this wave to propagate in, right, which is from right to left, to sort of go back and forth between these two mirrors. And so eventually you'll have lots and lots of photons that are being emitted via stimulated emission in order to make this laser actually be able to laze. All right, this is a really cool process. If that was confusing to you, I highly suggest that you try and create a laser in this applet from the PhET simulation website out of Colorado. Just try the one atom tab, follow these steps, and I think you'll find it hopefully very explanatory. Okay, I am going to leave it here for today, and we'll start in with more components of optical spectroscopy instruments in the next video.